The drift velocity is the flow velocity that a particle, such as an electron, attains due to an electric field. It can also be referred to as axial drift velocity. In general, an electron will propagate randomly in a conductor at the Fermi velocity. An applied electric field will give this random motion a small net flow velocity in one direction. In a semiconductor, the two main carrier scattering mechanisms are ionized impurity scattering and lattice scattering. Because current is proportional to drift velocity, which in a resistive material is, in turn, proportional to the magnitude of an external electric field, Ohm's law can be explained in terms of drift velocity. The most elementary expression of Ohm's law is, where U is the drift velocity, I1/4 is the electron mobility of the material and E is the electric field. Experimental measure. The formula for evaluating the drift velocity of charge carriers in a material of constant cross-sectional area is given by where U is the drift velocity of electrons, J is the current density flowing through the material, N is the charge carrier number density, and Q is the charge on the charge carrier. In terms of the basic properties of the right cylindrical current-carrying metallic ohmic conductor, where the charge carriers are electrons, this expression can be rewritten as where U is again the drift velocity of the electrons, in Mars R1, m is the molecular mass of the metal, in kg, IV is the voltage applied across the conductor, in V, I is the density of the conductor, in gamma 3, E is the elementary charge, in C, F is the number of free electrons per atom, A is the length of the conductor, in M, I florin is the electric conductivity of the medium at the temperature considered, in SM. Numerical example, electricity is most commonly conducted in a copper wire. Copper has a density of 7008940000000 unregistered trademark 8.94 grams per centimeter 3, and an atomic weight of 699863546000000 unregistered trademark 63.546 grams per mole. So there are 70051406855000000 unregistered trademark. 140,685.5 moles per meter 3. In 1 mole of any element there are 7023602000000 unregistered trademark 6.02a, 1023 atoms. Therefore in 70001000000 unregistered trademark 1m3 of copper there are about 70288500000 unregistered trademark 8.5a, 1028 atoms. Copper has 1 free electron per atom, so N is equal to 70288500000 unregistered trademark 8.5a, 1028 electrons per cubic meter. Assume a current I equals 3 amperes, and a wire of 69971000000 unregistered trademark 1 mm diameter. This wire has a cross-sectional area of 69937849999999999 unregistered trademark 7.85a, 10^7m22. The charge of one electron is Q equals 3018840000000 unregistered trademark a 1.6a, 10^19c. The drift velocity therefore can be calculated. Dimensional analysis. Therefore in this wire the electrons are flowing at the rate of 3003720000000 unregistered trademark a 0.00028 meters per second. By comparison, the Fermi flow velocity of these electrons is around 7006157000000 unregistered trademark 1570 km per second. In the case of alternating current, the direction of electron drift switches with the frequency of the current. In the example above, if the current were to alternate with the frequency of f equals 70016000000 unregistered trademark 60 Hz, drift velocity would likewise vary in a sine wave pattern, and electrons would fluctuate about their initial positions with the amplitude of. See also, flow velocity, electron mobility, speed of electricity, drift chamber, guiding center. References: Griffiths, David. Introduction to Electrodynamics. Upper Saddle River, New Jersey, Prentice Hall. Pages 289. http 230 NSC15 AST ARGSU EduElectric Ohmic HTML Ohm's Law, Microscopic View, retrieved February 14, 2009. External links: Ohm's Law, Microscopic View at Hyperphysics.